Welcome back to the 21st video of this course on quantum processing. Today I will talk about a new quantum phase transition, not thermodynamic, but you will see in a second why it's called a phase transition. This elusive interface between classical mechanics and quantum mechanics we will see now when upon this treatment. Now consider you have a classical system. Okay, this classical system obeys our thermodynamic description of equipartition theories and equilibrium statistical mechanics, that it will thermalize, it will go to thermal equilibrium after some time that you will let the system evolve. Here the system can be considered as a reservoir, as a bath, as a heat bath that you can thermalize your parts with, and also is coupled to the environment. Maybe if it's closed, it can still thermalize once it couples to the or it's put in an environment that has to make its parts go to the ground state of the classical hydrodynamic description. Here let's consider a quantum system. So quantum systems are really different at some point, to be honest. So not all the quantum systems that you can play with can go to what we call the non-thermalizing effect. So you ask yourself, is it thermalizable? I can tell you at some point that this is non-thermalizable state, and you can actually have many persistent information inside this quantum system. So this quantum system you can consider as maybe, for example, some spins that you have, some fermion or bosons, at some atoms, maybe also some quantum information perspective of a qubit. You have superposition of different spatial configuration here. So, and whatever kinds of quantum systems that you have. So you can imagine that we bring those systems to be in a non-thermalizing effect. So you can have persistent information along the whole subsystems of these important quantum degenerate or non-degenerate system counterparts or parts in the system here. So let's see something about this interface between classical description of matter, or quantum description actually. So at some perspective of the thermalizing effect, if you have a thermal phase and you start to compare it with what we call the many-body localization, and we will see what is exactly this many-body localization once we talk about quantum systems. So let's just first put it in a pinpoint here that you can have a thermal effect and a non-thermal effect, and this exists in this many-body localized systems. In fact, this many-body localization has been pioneered by Emmanuel Bloch. He was one of the first people to observe this kind of experimental fact for this many-body Anderson localization. We call it for Anderson. It's related to Anderson. You'll see in a second. Let's consider some important thermodynamic description of a density matrix for a closed system. For example, if you have a density matrix that will evolve over time, and you have here the kinds of wave functions for the Hamiltonian, this closed system for the Hamiltonian, and in fact we can sometimes call this flocate quantum system, flocate system also, which preserves the unitarity and locality of the dynamics, and you just take the density matrix at some time and you evolve it unitarily over time between system and the other, well, with just time evolution of your density matrix, for example, as you see here from this flocate quantum system, flocate system description in a density matrix. Here, if you see the non-thermalizing effect, so if you have thermalization, your density matrix can be expressed by this partition function, just normalizes probability of this kind of exponential over the partition function, but this can be considered as a thermalizable effect. If it's really not thermalizable effect, that you have this relation is damaged. Okay, so the density matrix can be no longer expressed by this way, and we call now this kind of non-thermalizing effect as a hidden information in your system. So you can in fact have thermalizable effects inside the subsystems of a quantum system. Let's consider this system, for example, a quantum system. You have many subsystems, A, B, C, D, and E, whatever. So at whole, the system fails to be a heat bath for itself, but it has many entangled states inside, and each entangled state, each subsystem can thermalize by itself. So the density operator, you trace it over the whole subsystems. Okay, so the subsystems will thermalize, but the whole system does not thermalize. So you can see here hidden information at the density matrix beginning at t equals 0, and then you evolve along the subsystems, and in these kind of quantum entangled subsystems in your whole system of a density matrix described by the time evolution of itself here. So you can time evolve the density matrix at infinite time. So let's see how it will work after time equals to infinity, as you can see here. So the density matrix of subsystem, this is a reservoir for itself, and this is different from talking about the whole system. Okay, so now it's subsystems physics, as we see. There is an important also definition for eigenstates of your many-body system. Let's see how, because it's, okay, this is a hypothesis, we call it eigenstate thermalization hypothesis, but it works well when we try to compare this Anderson localized systems and the other thermalizing systems or thermalizing phases. So if you have a system, okay, like this, that's just to trace out the whole parts or counterparts behind A and just focus on A. So the density matrix for A, so it's now a thermal density matrix that you can write down ordinarily by this partition function. And this density matrix, if you take the trace of the density matrix, you can recover actually the entropy. Density matrix, Len density matrix, as you can see. And this entropy on the subsystem A, actually it grows as the volume of a dimension here, L. Say that this is L. Okay, so it grows, we call it the volume law entanglement dependence. It's called volume law entanglement of the entropy for the eigenstate thermalizing effect. Here it's only one single eigenstate that can work very well. We call it extreme level of the whole microcanonical ensemble of the system, and just single eigenstate can be enough to identify this thermalization hypothesis, as you see. And also this density matrix can also just basic for density matrix. You can write down this for the single eigenstates or the Fock state representation of your number state in the trace of whole these systems. For A, you retrieve the density matrix. So the important thing here to remind you that this thermalization hypothesis, when it comes to the MBL transition here, the many-body localized systems, we call it many-body Anderson localized systems, there is a failure of this eigenstate thermalization hypothesis. So this is the quantum phase transition that I told you, the quantum phase transition in terms of the dynamics, but not the phase transition. So not thermodynamic phase transition, actually. This is just the dynamics. We'll get to the model here. So this is a model for the Fermi-Hubbard model. We previously mentioned the Hubbard model for our Bose-Einstein condensate case for the Bose-Hubbard model, and now the Hamiltonian that looks like this for the Fermi-Hubbard model. So there are no big differences that you can see. Just you have the same U and J. You have two spins for two Fermi gases. You have two fermions on the lattice, and you just have this difference, the whole difference here in this quantum random disorder distribution that we are going to study our many-body localization with here. So imagine that you have superimposed two overlapping wave functions for lattice, actually for two optical lattices together overlapping two optical lattices. You can see that this is responsible for this term for the sinusoidal oscillation here. So let us start out our journey for the many-body localization. So you have couples of charges distribution on a lattice. We call it charge density wave, and the technical term. You have three kinds of phases that we can cover here. The first phase that we call it Aubrey Interphase, suggested in 1980s paper by Aubrey and Andra and annual reviews of Israel Society, and this is for that you don't have the interaction. So the on-site interaction is zero. You cancel out the couples of interactions that exist on an on-site lattice. So here you have two overlapping lattices. So this is the disorder, okay? Disordered systems that we are going to tune around this transition. Another phase, we call it ergodic phase. Ergodic phase, and let's look at this here. We call it ergodic phase because the ratio of the disorder over the kinetic energy, if you have the ratio of disorder to the kinetic energy is less than 2, you can evolve the delocalized system. So you can think about it for a moment. If you have this less than 2 and if it's larger than 2 for this, the other phase, for we call it non-ergodic phase. So non-ergodic phase means that you start to delocalize the system, because a quasi-random disorder here, we evolve the system in a quasi-random fashion. Over the kinetic energy is larger than 2, it means that the kinetic energy is hugely suppressed in comparison with the ergodic phase. So you have here the ergodic phase, you have delocalized the system over the lattice, okay, over even, odd, even, odd, even, odd lattice sides. So here you have extension. And for the non-ergodic phase, you have the mini-body localization effect here. Here you have localization, and I mentioned here this is the localization effect. So here you just extend over the lattice sides. And actually, if you evolve the system, the eigenstates, you evolve the eigenstates of the system from 0 until from 0 to 2, so you have to end up with 2 at infinite interaction. So infinite interaction means that the system actually can return to its initial distribution at the 0 u here, and this is actually was confirmed by many studies in this mini-body localizing effect. Let me tell you also that you can evolve the system and you increase the on-site interaction, you increase the interaction, you can go to the delocalizing effect. And this is one way also to go from the mini-body localization to the delocalization, when you start to increase the ratio of U over J, meaning that you increase the on-site interaction. You can go from non-ergodic phase to ergodic phase of this model here. One thing also to mention, this is one of the main observable effects here, the observable for our system here, we call it imbalance. The I here is imbalance. This imbalance is the ratio between the number of the charge density waves in the odd here and the even minus the odd, even, odd, as I told you, and you just have the imbalance of this ratio, or the difference over the summation. So if you have the imbalance equals 0, means that you have the even number of distribution is equivalent to the odd distribution of this kind here. And it means also that, let us look at this figure. It means also, as you look at this figure from Schreiber paper in 2015, I'd like to recommend you to check it out if more details are interesting for you, that you can evolve the system here. It's a 0 point, so the imbalance equals 0 means that you are on the ergodic phase. So it means that you have complete delocalization over the lattice sides here, and once you evolve the system and you increase the quasi-random disorder of the system over the the kinetic energy term, you can go to MBL. So you can go to non-ergodic phase, you can localize the system once you just play with the disorder of the eigenstates of your charge density wave of this important figure here, just representing the transition from the delocalizing effect, the delocalizing phase, to the MBL phase, from the ergodic phase to the MBL transition, many-body localized, many-body Anderson localized systems. This MBL phase has attracted a lot of attentions in the field of condensed matter physics, non-equilibrium dynamics, quantum simulation. People are trying even now, and Emmanuel Bloch successfully did this order in 2D. So he studied the imbalance that we covered here in 1D problem in 2D. So I will link you to the paper if you're interested to study more upon this. I will link you to the paper in the description of this video. So let me tell you that quantum phase transition, these kinds of quantum phase transitions in the many-body physics have just people in different fields like quantum information theory building for entanglement frontiers, the elusive interface between the ETH, maybe eigenstate normalization hypothesis I talked about, to the MBL phase transition, to the MBL phase description of quantum systems, quantum many-body physics. So one last thing I would like to mention here for our MBL case is that many theories and many experiments have been hand in hand together going for better description of nature, or better description of the deviation from classical hydrodynamic description of matter and a quantum thermalization effect, as you saw in this video, that you don't have thermalization in quantum mechanics, you just have quantum thermalization, and even more, as I told you, the thermalization of subsystems, so entangled subsystems that it will evolve over time. So with this quantum simulation problem, I'd like to end up this video, and thank you very much for your attention, and see you in the next time.